Hello everybody, this is the second lecture for chapter 10 of the statistical learning course. So in the first part we've discussed maximal margin classifiers for binary classification, where for a given data you try to find a hyperplane which separates the predictor space into two. So points lying on one side of the hyperplane are classified in one class called 1, and points on the other side of the hyperplane are classified as class minus 1, being the other class. And we mentioned that we have an optimization problem which tries to find the best hyperplane, which classifies all observations correctly, but which also tries to maximize the smallest distance between any data point and the hyperplane, so has to gain the highest confidence about our classifications. And at the end of the first lecture, we said that we won't outline the steps for optimization, we leave that out of scope. But now we're going to identify weaknesses of this approach, and that one of the main problems uh, is the main problem possibly is the non-robustness of this method with respect to some noise. So for example, let's say this is our data set and this is our maximal margin classifier. But what happens sometimes if you only add a single point to your data? So let's say this new blue point here was added. Then we see that if we add a single point, the separating hyperplane completely changes. So by adding one point to your data, you have a drastically different result. And this is not very desirable because all the bias variance dilemma we've outlined in earlier chapters applies here. So if you have very volatile predictions, this is not good for your prediction ability out of sample. So there's a need to try to stabilize predictions or classifications made by the maximal margin classifier, and we're going to discuss approaches to remedy this problem subsequently. Okay, so this is one issue, and then another issue is that for many data sets, there might exist zero or no hyperplane which is able to correctly classify all observations. Okay, so sometimes there exists no separating hyperplane. Okay, so in the previous optimization problem we've outlined, sometimes cannot yield any solution for m greater than 0. So for this reason, we now introduce a generalization of maximal margin classifiers, which leads to a hyperplane which almost separates the classes. So it doesn't exactly separate the two classes, but it almost separates them perfectly. So this generalization of the maximal margin classifier is known as support vector classifier. And the idea here is we're going to introduce instead a soft margin where instead of allowing no observation to be inside the margin, we're going to allow for some of the observations to um, to be in the margin or even be on the wrong side of the hyperplane. But to do that, we'll allow for a budget of violations. Okay, so we'll impose that the amount of violations of the of observations being on the wrong side of the hyperplane or being within the margin should not be too much. Okay, so some observations can violate it to a certain extent, but we're gonna impose a cap on the amount of violation that occurs. Okay, so the idea here underlying this is again it's the bias variance trade-off where it might be worthwhile to misclassify a few observations if it gives us more stability and more volatile predictions for out of sample observations. Okay, so we're trying to reduce volatility or non-robustness by allowing for some misclassification. Okay, and before that, the quick idea we saw last time that the maximal margin classifier only depends on really a few support vectors. Well, the idea is when we're going to allow for some violation, we're going to see that the number of support vector increases. So instead of the classifier depending on only 3 points, it might depend on more than that, let's say 10 points or something like that. And the property to depend on more points reduces the variance of the classification and thus might give more accurate predictions out of sample. So we now introduce more formally the problem associated with the support vector classifier. So once again, we try to find a hyperplane characterized by beta 0 until beta p, and m being the what we call the size of the margin, so basically the distance between the hyperplane and observations. And moreover, now we're going to introduce new variables, epsilon 1 until epsilon n, which are called slack variables and which will allow for violations of the margin we've identified earlier. Okay, so we want to maximize m, the distance between the hyperplane and observations, such that. So first, again, the sum of squared betas will be equal to 1. So this unit norm is imposed to first preclude having m arbitrarily large through simply scaling the betas, so to ensure the problem is well posed. And moreover, this will allow us to interpret this quantity here as a distance between the hyperplane and predictors of observation I. Okay, so we want to find and have that the norm of the vector beta, excluding beta 0, is 1. We want to have this. So here this looks pretty much like what we had before with a slight modification. Okay, so we said that this quantity represents the distance between a point and the hyperplane. And here, when we multiply by yi, this quantity, if we had a separating hyperplane, this had to be always greater or equal to 0. And if we wanted to impose that the distance was at least m, then this quantity needed to be at least greater or equal to m. But now the novelty here is we add 1 minus epsilon I, and the epsilon i's, when they're greater than 0, this will allow for a violation. Okay, so here, if epsilon is 0, it means that the distance between point xi and the separating hyperplane is greater or equal to m. Okay, so when this guy is not there, the distance is at least m. But when epsilon is greater than 0, this means that we can have a smaller distance between the hyperplane and the point. Okay, so if epsilon is between 0 and 1, it means that the point is within the margin. So it's closer than m, but still on the right side of the hyperplane. And if epsilon is greater than 1, it means that this observation I is on the wrong side of the hyperplane. Okay, so we see that including the epsilons allows for a violation of the margin. And let's just maybe do a picture to illustrate what we mean by the margin. So let's say this was the separating hyperplane, and we had, let's say, the margin here. So here, oops, it's not, sorry, these should be equally as far away from the middle line. I'm just not good with drawing. So the distance between this and this should be m, and the distance between this and this should be m. And the idea here is that in the original maximal margin classifier, no points would be inside the margin, and the support vectors would be exactly on the margin. Okay, so something like this, for example. So in the maximal margin classifier, no point violate the margin in the sense that the support vectors are on the margin but are never inside and never on the wrong side. Okay, so um, what happens now when we include the epsilons, if epsilon is between 0 and 1, it would mean that for this, the data point I, the data point would be inside the margin. So it would be kind of violating the margin. And if epsilon is greater than 1, then the point would be on the other side of the margin. Okay, so we see that in using this an equation means that when epsilon is non-zero, we would allow this point to violate our hyperplane. But the idea, as we said, we don't want to impose, to allow for arbitrary violations of the hyperplane. We want to limit the occurrence of these violations. So the idea here is we're going to cap the epsilons. Okay, so epsilons, they're always greater or equal to 0, but we're going to impose a constraint on the sum of epsilons. Okay, because we said when epsilon is strictly greater than 0, it's a violation. And the greater epsilon is, the greater the violation is. So to reduce the possible amount of violation, we will impose that the sum of epsilon I is smaller or equal to some constant c. So C acts kind of as a budget for violation, means that if C is equal to 0, then you allow for 0 violation, but if C is large, then you would allow for a lot of violations because the sum of epsilons can be large, so many epsilon can be non-zero. And C in practice, it's a tuning parameter or a hyperparameter. So exactly like hyperparameters or tuning parameters seen in earlier chapters. So for example, in KNN, the parameter K or something like that, the number of predictors in the linear regression. This C here is not decided on at the, well, we present the problem for a fixed C, but how to choose C in practice, we need to try different values. And the idea here is often to choose this capital C through cross-validation to see what leads to the best performance. Okay, so in a nutshell, the support vector classifier is similar to maximal margin classifier, except that we allow for some violations of the margin or the hyperplane through these epsilons, but we cap the sum of epsilons not to so as to limit the amount of violations that can occur. Okay, and once again, how do we do the classification? It's exactly the same as before. So if we have a new data point whose predictors are x0, then we can compute, to classify it, we can compute f of x0 being the linear combination of the predictors based on betas, which are characterizing the optimal hyperplane of the support vector classifier. And depending on the sign of fx0, it's going to tell us on which side of the hyperplane this observation falls, so how to classify it. And the magnitude, so the absolute value of f of x0 tells us how far away is this observation from the hyperplane, so it gives us a measure of confidence about our prediction. Okay, so as we said, when the capital C parameter is strictly 0, then it means that all epsilons are 0 and we allow for no violation of the margin or the hyperplane. Okay, so in that case, the support vector classifier falls back on the maximal margin classifier. And as we just discussed, whenever epsilon I is between 0 and 1, with 0 included, it means that observation I is on the right side of the hyperplane, okay, but it's within the margin, which wasn't allowed previously. And when epsilon I is greater than 1, it means that the observation is on the wrong side of the hyperplane. So this training observation is misclassified by the optimal hyperplane. Okay, so the epsilon i's, they're often called slack variables. Okay, so as we said earlier, capital C is a hyperparameter determining the tolerance for margin violation. Okay, so because C bounds the sum of epsilons, if C is very small, then all epsilons have to be very small, and the uh, support vector classifier doesn't allow for a lot of variation. Okay. Conversely, if capital C is high, then there's a lot of violations of the margin or the hyperplane possible. Okay, so we see here that capital C drives the bias variance trade-off of the optimization. Okay, so when C is very small, you have a very good fit to the training data because you don't misclassify no observation. But the idea here is when C is very small, uh, we're we're gonna see shortly that your your high optimal hyperplane depends on a very low number of support vectors, and depending on very few observations mean low robustness, because if you slightly change these observations, you might get a totally different hyperplane. Okay, so small c entails also high variance of predictions. Okay, so in practice, c is chosen through cross validation to determine what's the um, amount of robustness you mean to suitably reduce variance, but still being sufficiently accurate not to misclassify too many observations. Okay, so another benefit of adding this c greater than 0 is this would allow for solutions of the optimization problem even if no separating hyperplane exists. Because let's say we have this data, so this figure is drawn from the ISL textbook again. Let's say we have this data set, then it wouldn't be possible to separate the blue observations from the pink one. But we see that uh, with this support vector classifier, if we allow some violations, so for example 12 is on the wrong side, 11 is on the wrong side here, but if we allow for some violations, we can see that we could still have a reasonable hyperplane doing somewhat well for observations, but which doesn't classify all observations correctly. Okay, so if we allowed for no violation at all, we wouldn't get a solution, and wouldn't be possible to get a classifier for this data set. Whereas when we allow for some degree of violation of the hyperplane, then we can see we can obtain a solution to the previous optimization problem, provided that C is large enough. Okay, so if C is very close to 0, we still might get 0 solution, but as we increase C, at some point there will be a solution which starts to exist. Okay, so again, here the this is a bit analogous to the maximal margin classifier. For the support vector classifier, the optimal hyperplane depends only on some of the data points. So it depends only on data points that are exactly on the margin or which violate the margin. So violate the margin would mean inside the margin or on the right side or on the wrong side of the hyperplane. Okay, so the set of all such points which either violate the margin or are exactly on the margin, they're known as support vectors once again. Okay, so in maximal margin classifier, you didn't have any violation, so only the points exactly on the margin were support vectors. But now the support vectors also include points which violate the margin. And why is this the case? It's because points which violate the margin, they have an impact because they need to consume some of the budget of the epsilon. Okay, so if you change the location of points violating the margin, they might either need a higher or a lower epsilon, and by adjusting the epsilon for this observation, you might also give some slack for other observations for violations, so this would change the optimal solution. So here, what this means is that for any support vector, if you change their location, you're going to change the optimal solution. Conversely, for all points that are not support vectors, so that are not violating the margin and far away, not on the margin either, so are further away from the margin, then if you slightly alter their location and they're still outside the margin, then the optimal solution doesn't change at all. Okay, so the solution or optimal hyperplane only depends on the support vectors, which are data points whose predictors lie either on the margin or do violate the margin. Okay, so again, this supports our assumption that capital C drives the bias variance trade-off, because when we allow for more violation, then we'll have more data points violating the margin, so more support vectors, so the optimal hyperplane will depend on more data point. And having a classifier which depends on more data points reduces its robustness. So you're not relying on only on a single precise data point, you're relying on a set of points which has the property of dampening the noise with the impact of noise on each individual data points. So we can see that when C is large, you have more violation and the margin is wider, and you have more support vectors, so more stability. Okay, so let's let's not illustrate that right now. We'll show that later. But here, this also will. Okay, let's switch slide. This also highlights a key difference between discriminant approaches and the support vector classifier approach. Okay, so let's say we consider linear discriminant and support vector classifier. Both methods use a linear boundary, okay, a linear decision boundary. Okay, so if you're in R2, for example, you're in two-dimensional space, then the predictor space is divided by a straight line, both with linear discriminant and the support vector classifier. However, for the support vector classifier, the solution only depends on the data points on the margin or close to the hyperplane, okay, or violating the hyperplane. Conversely, for a linear discriminant analysis, all data points have an impact on the classifying hyperplane, okay, because even points that are far away from the decision boundary, they will impact mu k and sigma k, which is basically the parameter estimates for the distribution of predictors in each of the classes. So all data points impact the mu vector of mu and matrix sigma, which drive the Gaussian distributions from which predictors were generated in each class. So we see that even points far away from the boundary have impacted the solution. Okay, conversely, for support vector classifier, as we said, points far away, they have zero impact on the solution. So if you change the location of points that are far away, no impact. Okay, in contrast, what happens with a logistic regression? Is it like linear discriminant or support vector machines? Well, it's different from both, but we can see in that perspective, logistic regression acts a bit more like support vector machines than linear discriminant, in the sense that it's possible to show, so we won't do that here. Again, this is out of scope. You can have a look at the textbooks if you want to have further details on this, but it can be shown that logistic regression has very low sensitivity to observations far away from the decision boundary. Okay, so for support vector machines, points that are far away from the boundary have zero impact. For linear discriminant, points that are far away do have some impact. And for logistic regression, points that are far away have limited impact. So in that sense, logistic regression has a behavior which might be a bit more similar to support vector classifier than linear discriminant analysis. And this is interesting because all these methods, logistic regression, LDA, support vector classifier, they all give a linear decision boundary. So you might be wondering, why would I use one versus the other? But even if they use linear decision boundaries, they don't produce the same boundary due to the assumptions underlying these models being different. Okay, so for example, linear discriminant analysis is a parametric model where you assume normality of predictors in each class, whereas for support vector machines, there's no parametric assumption at all. Okay, for the logistic regression, you assume the presence of a logistic link. So this is also an assumption that is not there in support vector classification. Okay, so as we said, when you increase C, you allow for more violations of the margin. So this has the impact of also increasing the margin size. So because you're able to violate the margin, let's increase the margin size because it's possible in that case. So we can see that the larger C is, the larger the margin is. Okay, the margin is the value of M solving the optimization problem. So here, this is the same data set, and we see here if C is super large, then the margins are super large here, and a lot of points lie within the margins on both sides. And as you reduce C, we can see that the margins, they become closer and closer to the optimal hyperplane. And of course, the hyperplane changes every time you change C, but the margins are tighter around the hyperplane. And you have, as you shrink C, you have less and less observations violating the margin. Okay, but we see here when C is super large, basically all the data points, they fall into the margin. Okay, so it means that there's a lot of support vector, and the prediction, the hyperplane or the optimal, the solution of the problem is much more robust than in that case here, where probably if you change a few of these data points, you get an answer which can vary a lot. Okay, so as we said, when C is large, the margin is very wide. There's a lot of support vectors. When C is small, the margin is very small, very few support vectors. Okay, that's great. We'll stop here and we'll have one last video for the next lecture. So thanks for listening and see you next time.